In this section, I'm going to consider the region of convergence of the Laplace transform in more detail. In particular, I'll be introducing a number of key properties of the region of convergence. Since the region of convergence is a fundamental part of the Laplace transform, knowing some of the properties of the region of convergence is immensely helpful when working with the Laplace transform. Before I can discuss the properties of the region of convergence, I first need to introduce a few concepts and definitions. First, I need to introduce the definition of a left half plane. The set R of all complex numbers S satisfying a relationship of this particular form here for some real constant A is said to be a left half plane, which is abbreviated by the acronym LHP. In other words, a left half plane is a set of points in the complex plane that lie strictly to the left of a vertical line. Two examples of sets that constitute left half planes are shown in the figures at the bottom of the slide. Clearly, the set denoted by the shaded region in each of these figures is comprised of all points in the complex plane that lie to the left of a vertical line. Next, I need to introduce the definition of a right half plane. The set R of all complex numbers S satisfying a relationship of this particular form here, where A is a real constant, is said to be a right half plane, which is abbreviated by the acronym RHP. In other words, a right half plane is a set of points in the complex plane that lie strictly to the right of a vertical line. Two examples of sets that constitute right half planes are shown in the figures at the bottom of the slide. Clearly, the set denoted by the shaded region in each of these figures is comprised of all points in the complex plane to the right of a vertical line. Next, I need to define the intersection of sets. For two sets A and B, the intersection of A and B, which is denoted as A cap B, is the set of all points that are in both A and B. An example of set intersection is shown in the figures at the bottom of the slide. For the sets R1 and R2 shown in the leftmost and middle figures, the intersection of R1 and R2 is the set shown in the rightmost figure. Observe that the points in the intersection of R1 and R2 are all of the points that are in common to both R1 and R2. Next, I need to introduce the operation of adding a set and a scalar, such as a complex number. For a set S and a scalar constant A, the notation S plus A denotes the set given by this particular formula here. In other words, S plus A is the set formed by adding A to each element of S. Effectively, adding a scalar to a set applies a translation, in other words a shift, to the region associated with the set. An example of the addition of a scalar to a set is shown in the figures at the bottom of the slide. For the set R shown in the figure on the left, the set R plus 1 is the set shown in the figure on the right. Observe that the set R plus 1 is essentially the set R shifted rightward by 1. Next, I need to introduce the operation of multiplying a set by a scalar, such as a real or complex number. For a set S and a scalar constant A, the notation AS denotes the set given by this particular formula here. In other words, AS is a set formed by multiplying each element of S by A. For two complex numbers A and Z, multiplying Z by A affects Z by scaling by the magnitude of A and rotating about the origin by the argument of A. So effectively, multiplying a set by a scalar applies a scaling and/or rotation to the region associated with the set. In the case that A is real, a rotation only takes place when A is negative. And since the rotation is by pi in this case, the end effect is that the region associated with the set appears flipped left to right. An example illustrating the multiplication of a set by a scalar is shown in the figures at the bottom of the slide. Suppose that the set R is as shown in the top middle figure. Then the sets 2R and minus 2R are as shown in the bottom left and bottom right figures respectively. In the case of the set 2R, the region associated with the set R has been scaled by a factor of 2. In the case of the set minus 2R, the region associated with the set R has been both scaled by a factor of 2 and flipped left to right. As we saw earlier, the complete specification of a Laplace transform big X requires not only an algebraic expression for big X, but also the region of convergence associated with big X. Since distinct functions can have identical algebraic expressions for their Laplace transforms, the region of convergence is important in order to be able to distinguish between such functions when represented in terms of their Laplace transforms. Since the region of convergence plays such a fundamental role in the Laplace transform, it's helpful to know some of the key properties possessed by the region of convergence. On the subsequent slides, a number of these properties will be introduced. The first property of the region of convergence that I need to introduce relates to the general form of the region of convergence. As it turns out, the region of convergence cannot have any arbitrary shape in the complex plane. In particular, the region of convergence of a Laplace transform always consists of strips parallel to the imaginary axis in the complex plane. More specifically, if a particular point is in the region of convergence, then all points on the vertical line through that point must also be in the region of convergence. So the region of convergence essentially consists of a collection of many vertical lines. Consider the three sets shown in the figures at the bottom of the slide. For each of these sets, let's consider whether it would constitute a valid region of convergence based on the property of the region of convergence that was just introduced. The sets shown in the two leftmost figures are comprised of many vertical lines and are in fact valid regions of convergence. The set in the rightmost figure is not comprised of vertical lines. Instead, this set consists of many horizontal lines. Therefore, this set is not a valid region of convergence. The second property of the region of convergence that I need to introduce relates to rational Laplace transforms. If a Laplace transform big X is a rational function, the region of convergence of big X does not contain any poles and is bounded by poles or extends to infinity. Since a rational function does not converge at its poles, it should be obvious that the region of convergence associated with such a function can't contain any of its poles. At the bottom of the slide are three figures, each showing a set in the complex plane. Let's consider if each of these sets would constitute a valid region of convergence for a Laplace transform that is a rational function. The set shown in each of the leftmost and middle figures constitutes a valid region of convergence. In the leftmost figure, the set is bounded by one pole on the left and bounded by two poles on the right. In the middle figure, the set is bounded by two poles on the left and extends rightward to infinity. The set shown in the rightmost figure, however, is not a valid region of convergence. This is due to the fact that the set is bounded on the right by a vertical line that contains no poles. The third property of the region of convergence that I need to introduce relates to Laplace transforms of finite duration functions. If a function little x is finite duration and its Laplace transform big X converges for at least one point, then big X converges for all points in the complex plane. In other words, the region of convergence is the entire complex plane. At the bottom of this slide are three figures, each showing a set in the complex plane. Let's consider if each of these sets would constitute a valid region of convergence for a Laplace transform of a finite duration function. The set shown in the leftmost figure is a valid region of convergence, since this set is the entire complex plane. The sets shown in the middle and rightmost figures are not valid regions of convergence for the Laplace transform of a finite duration function, since they don't contain the entire complex plane. The fourth property of the region of convergence that I need to introduce relates to Laplace transforms of right-sided functions. If a function little x is right-sided, and the vertical line real part of s equals sigma naught is in the region of convergence of the Laplace transform big X, where big X is the Laplace transform of little x, then all the values of S for which the real part of S is greater than sigma naught must also be in the region of convergence. In other words, the region of convergence is a right half plane, including the vertical line real part of S is equal to sigma naught. At the bottom of the slide are three figures, each showing a set in the complex plane. Let's consider if each of these sets would constitute a valid region of convergence for the Laplace transform of a function that is right-sided but not left-sided. The set shown in the leftmost figure is a valid region of convergence, since this set is a right half plane. The sets shown in the middle and rightmost figures are not valid regions of convergence, since they are not right half planes, and a right-sided but not left-sided function must have a region of convergence that is a right half plane. The fifth property of the region of convergence that I need to introduce relates to Laplace transforms of left-sided functions. If a function little x is left-sided, and the vertical line real part of S is equal to sigma naught, is in the region of convergence of the Laplace transform big X, where big X is the Laplace transform of little x, then all of the values of S for which the real part of S is less than sigma naught must also be in the region of convergence. In other words, the region of convergence is a left half plane, including the vertical line real part of S is equal to sigma naught. At the bottom of the slide are three figures, each showing a set in the complex plane. Let's consider if each of these sets would constitute a valid region of convergence for the Laplace transform of a function that is left-sided but not right-sided. The set shown in the leftmost figure is a valid region of convergence, since this set is a left half plane. The sets shown in the middle and rightmost figures are not valid regions of convergence, since they are not left half planes, and the region of convergence of a left-sided but not right-sided function must be a left half plane. The sixth property of the region of convergence that I need to introduce relates to Laplace transforms of two-sided functions. If a function little x is two-sided, and the vertical line real part of S equals sigma naught is in the region of convergence of the Laplace transform big X, where big X is the Laplace transform of little x, then the region of convergence will consist of a strip in the complex plane that includes the vertical line real part of S is equal to sigma naught. At the bottom of the slide are three figures, each showing a set in the complex plane. Let's consider if each of these sets would constitute a valid region of convergence for the Laplace transform of a two-sided function. The set shown in the leftmost figure is a valid region of convergence, since this set is a vertical strip. The sets shown in the middle and rightmost figures are not valid regions of convergence, since they are not vertical strips, and the region of convergence of a two-sided function must be a vertical strip. The seventh property of the region of convergence that I need to introduce relates to Laplace transforms that are rational and originate from transforming functions that are either left or right-sided. If the Laplace transform big X of a function little x is rational with at least one pole, then the following is true. If little x is right-sided, the region of convergence of big X is to the right of the rightmost pole of big X. In other words, the right half plane to the right of the rightmost pole. If little x is left-sided, the region of convergence of big X is to the left of the leftmost pole of big X. In other words, the left half plane to the left of the leftmost pole. Incidentally, the preceding property for rational Laplace transforms is implied by the combination of properties 1, 2, 4, and 5 introduced earlier. At the bottom of the slide are four figures, each showing a set in the complex plane. For each of the sets shown in the figures, let's consider if the set would constitute a valid region of convergence for a Laplace transform that is rational and originates from transforming a function that is either left or right-sided. The set in the left figure constitutes a valid region of convergence for the Laplace transform of a left-sided function, since this set is comprised of all points to the left of the leftmost pole. The set in the second figure from the left does not constitute a valid region of convergence, since this set contains one or more poles. The set in the third figure from the left constitutes a valid region of convergence for a Laplace transform that is rational and originates from transforming a right-sided function, since this set is comprised of all points to the right of the rightmost pole. Lastly, the set in the rightmost figure is not a valid region of convergence for a rational Laplace transform, since this set contains one or more poles. At this point, I'd like to make some additional comments about the general form of the region of convergence of the Laplace transform. In particular, I'd like to make some comments related to the left and right-sidedness of functions. Every function can be classified as either left-sided or not left-sided. Similarly, every function can also be classified as either right-sided or not right-sided. This leads to exactly 4 possible combinations of left and right-sidedness that a function can possess. The table at the top of the slide shows the form of the region of convergence of the Laplace transform big X of the function little x in the case of each of the 4 combinations of left and right-sidedness of little x. Since every function is covered by exactly one of these 4 cases, this implies that the only possible forms for the region of convergence are the 4 listed in the table. In other words, if the Laplace transform big X exists, the region of convergence of big X can only be of the form of a left half-plane, a right half-plane, a vertical strip, or the entire complex plane. Consider, for example, the 2 sets shown in the figures at the bottom of this slide. Neither of these sets constitutes a valid region of convergence. This is due to the fact that neither set is a left half-plane, a right half-plane, a single vertical strip, or the entire complex plane. At this point, I'd like to consider an example to show how we can use the various properties of the region of convergence of the Laplace transform to which we have been introduced. In particular, I'd like to consider example 7.7. In this example, we're told that the Laplace transform big X of the function little x has the algebraic expression given by this particular formula here. Notice that we're not given the region of convergence of big X. Then what we're asked to do in this example is to identify all possible regions of convergence of big X, and for each region of convergence indicate whether the corresponding function little x is left-sided but not right-sided, right-sided but not left-sided, two-sided, or finite duration. Before proceeding further, I'm going to pause in order to scroll the example upwards so that we can see the solution in its entirety. To begin the solution, we observe that the Laplace transform big X is rational. Therefore, the regions of convergence that big X can have are dictated by its poles. So we proceed to find the poles of big X by factoring big X into all linear factors. Since big X is already partially factored, this only requires factoring 2 quadratic factors. One of these factors can be handled using the quadratic formula, while the other can be factored by inspection. This yields the fully factored expression for big X, shown here. From this factorization of big X, we can see that big X has poles at -2, -1 minus j, -1 plus j, and 1. Since these poles only have 3 distinct real parts, namely -2, -1, and 1, there are only 4 possible regions of convergence that big X can have, namely these 4 regions here. These 4 regions of convergence have been plotted in figures A, B, C, and D, along with the poles of big X. At this point, I'd like to explain in more detail how these regions of convergence were obtained. So suppose that this particular point here that's marked by a red dot is in the region of convergence of big X. Then from the properties of the region of convergence, we know that all the points on this vertical line must also be included in the region of convergence. And because the function big X is rational, we know that this vertical line is going to grow leftward and rightward until it either hits a pole or goes all the way to infinity. So this particular vertical line is going to expand in the rightward direction until it hits this pole at -2, and it's going to expand leftward forever because there's no pole out here to stop the region from growing larger. So this is going to yield a left half-plane region of convergence, this shaded region here, which is to the left of the pole at -2. Suppose instead that this point that I've marked by a red dot here is in the region of convergence. Then, due to the properties of the region of convergence, all the points on the vertical line through this point must also be in the region of convergence. But because the function big X is rational, this vertical line is going to expand to the left and to the right until it either hits poles or goes all the way to infinity. So this vertical line will expand leftward until it hits this pole at -2, and it will expand rightward until it hits this pair of complex conjugate poles at -1 plus and minus j. This gives us this vertical strip region of convergence, which is shaded here. Suppose instead that we consider this point here that's marked by a red dot. Suppose that this point is in our region of convergence. Then all the points on the vertical line through this point must be in the region of convergence. And because big X is a rational function, this vertical line here will expand leftward and rightward until it either hits poles or goes all the way to infinity. So this vertical line will expand leftward until it hits this pair of complex conjugate poles at -1 plus and minus j, and the vertical line will expand rightward until it hits this pole at +1. So this gives us a vertical strip for our region of convergence. And then lastly, suppose that we consider this point here that's marked by a red dot as our initial seed point. If this point is in the region of convergence, then all the points on the vertical line through this point are in the region of convergence. And because big X is a rational function, this vertical line will expand leftward and rightward until it either hits a pole or goes all the way to infinity. So this vertical line will expand leftward until it hits this pole at 1, and it will expand rightward forever because there are no poles out here to stop the region of convergence from growing larger. So this will give us a right half-plane region of convergence to the right of the pole at 1. So we conclude that big X has 4 possible regions of convergence, namely the ones shown in the figures. In particular, the regions of convergence shown in figures A, B, C, and D correspond to these 4 sets here, respectively. Now that we've identified all of the possible regions of convergence of big X, we only need to determine whether the function little x corresponding to each of these regions of convergence is left-sided but not right-sided, right-sided but not left-sided, finite duration, or two-sided. First, let's consider the region of convergence shown in figure A. Clearly this region is a left half-plane. Since a left half-plane region of convergence is associated with the Laplace transform of a left-sided function, little x must be left-sided in this case. Now consider the region of convergence shown in figure B. Clearly this is a vertical strip. Since a region of convergence that is a vertical strip is associated with the Laplace transform of a two-sided function, little x must be two-sided in this case. Now let's consider the region of convergence in figure C. This is also a vertical strip, so by a similar logic, the function little x must be two-sided. Lastly, let's consider the region of convergence in figure D. Clearly this is a right half-plane. Since a right half-plane region of convergence is associated with the Laplace transform of a right-sided function, little x must be right-sided in this case.